Can you post it in the chat? That would be very useful for us to open.
Oh, yeah. Good idea.
Okay. So normally now it's recording on YouTube. So good morning, everyone, or maybe good afternoon or good evening. Welcome to a new virtual QISS seminar. And today we are very glad to hear Nick Huggett, who is going to talk about non-commutative geometry. So just to remind you of the format briefly, there will first be a talk by Nick during 30 minutes, and then there will be some questions and a discussion session. So if you have questions, very brief questions for clarification during the talk, then you can interrupt and ask it. But otherwise, please keep your questions for the end, for the discussion session. And you can also write your questions in the chat if you are afraid of forgetting them. All right, so Nick, that's for you.
All right, thank you everybody for being here, and thank you so much to the organizers for organizing this. I want to sort of add that this is from a joint paper by myself, and then Fidele Lizzi and Tushar Menon. Fidele, I know is here. I haven't seen Tushar, but I don't see everybody, so maybe he's down on the list.
I'm here, Nick.
Hey, okay. So Tushar and I mean, Fidele is a philosopher and a physicist, so he certainly contributed to the philosophical parts, but more to the physics parts. Tushar and I contributed more to some of the philosophical parts. We're all here, and so when you ask questions, you'll get one of us, or one or more of us, answering, I guess, depending on who's the most authoritative on the question in hand. About the title, missing the point in non-commutative geometry. Well, it was supposed to be a little joke, I guess, but it's the argument that we're going to be making, or what we're trying to clarify is the sense in which there are no points in non-commutative geometry. So please take it that way. We're not at all the first to sort of suggest this, and I think maybe it's a sort of orthodoxy when people think about non-commutative geometry, or many people sort of think this way. But the aim of the paper and the talk is to kind of clarify the arguments for that conclusion and give some illustrative examples in the physics of why this is the case. So this isn't supposed to be a kind of dramatic new result kind of talk, but a sort of conceptual clarification talk, akin to sort of philosophical work. Okay, I'm not sure if everybody knows about non-commutative geometry, so there'll be a certain amount of setup of what non-commutative geometry is. And so, but time is limited, so it'll be pretty brief. But the first thing to realize is that, okay, so I have to do that. Non-commutative geometry is a deformation of classical geometry. So first of all, we'll set up the classical geometry, even though the things we'll say are somewhat trivial seeming. For instance, that classically the coordinates commute, because that's exactly what we're going to be deforming. Okay, so we're going to probe. Our question is, whether points are physically meaningful in non-commutative geometry, and so we have to have a mechanism, a strategy for approaching that question. And the way we do it is through the question of particle localization. So the extent to which there are points or regions below a certain scale is to be cashed out in terms of whether one can localize particles to points or below a certain scale. So to set that up, well, we'll take it as read that physical limitations always prevent us from ever perfectly localizing a particle. There's always going to be ignorance in the particle state. So the natural way to represent its state is with something like a Gaussian. This is an epistemic state. There's a spread, not because the particle is itself spread, but because there's an uncertainty. We have uncertainty in its position, and a normalized Gaussian is a natural way to present this. Let me note in the classical cases, we'll just to keep the equation simple, work in one dimension. When we go to the non-commutative case, for obvious reasons that you'll see, we have to work in 2 dimensions. But okay, but in 1 dimension, we'd represent the state like this. But even though there's always going to be uncertainty in the position of a particle, points are still going to be physically significant because there's no there's no finite limit to how localized they can be in this sense. Okay, but once we have a state, so that's what we'll just explain briefly now. I mean, pretty obvious point. But given the state, we can calculate expectation values. So for instance, of course, for position, the expectation value is x0, the center of the Gaussian, and the uncertainty, well, we can calculate the x squared to find the uncertainty, and it's basically alpha, which is the width of the Gaussian. And of course, there's uncertainty here because we're just ignorant about where it is. Okay. But what's clear from this setup is as we measure the particle or prepare the particle in a more and more localized way, this can all be taken without limit. Alpha can go to 0. We can basically point localize. There's no problem occurs with taking narrower and narrower Gaussians. And so in that sense, there's no smallest area, no smallest distance. And in that sense, we can go all the way down to points. This very simple, sort of familiar picture is, of course, what breaks down in commutative spaces, and the talk is exploring how it breaks down. All right, so that's classical particle position. Now we run the same kind of analysis in a non-commutative space. So we're going to consider we're considering a very simple example of non-commutative space where we'll just work in 2 dimensions and impose non-commutation between the coordinates. But this is a simple, there are more, as I'm sure most of you know, this is just a simple sort of boiled down case of versions of non-commutative geometry that have more real physics in them, ultimately something like, cons, spectral triples, and the points we're making would apply in that case too. We're just going to work in this very simple case. Okay, so I'm going to make a few remarks that are something of an aside on terminology, but I think it's worth taking a little time because the terminology can be confusing and to some extent people use it differently and it's a little controversial, and we want to sort of flag that. So because of this non-commutation, it makes sense to, sometimes we're going to call what we're talking about quantum space as well as non-commutative space. However, it's not quantum there's a certain senses in which it's not fully quantum. There's no H bar involved. I mean, you could set this theta to the Planck area and then there would be an H bar involved, but we're not assuming that. Or I like to think of it in this more precise way. Once we have this geometry, one can introduce dynamics into it. One will still have an action. But once one has the action, there's a choice. You can either go classical, but in this non-commutative space and demand that the action satisfies Hamilton's principle, or one can equally well take the action and demand that it satisfies Feynman's principle. In other words, it enters into a path integral and we go fully kind of quantum. So actually the things we're talking about aren't dependent on this particular choice of how the dynamical systems are behaving. But I want to apply, although we're calling it quantum space, one can now put sort of fields into it and they can behave either in this classical least action Hamilton way or quantumly in a quantum way according to Feynman. So just so you understand what quantum space means. And as I say, the community people actually use the term in different ways. We're happy to call it quantum space here because sort of pedagogical, heuristic purposes, because it'll emphasize for people who are coming to this that the familiar quantum formalism will apply. And so we will help ourselves to that. And also you'll see it'll become clear much of the kind of standard quantum interpretation will also be applied to quantum space, particularly when it comes to probabilities. So the first example of that is if we're going to apply the quantum formalism, thinking the non-commutative space through in familiar quantum terms, there's going to have to be a quantization map between classical functions and non-commutative operators. And I'm going to write these down, and you can see they're inspired. If I have by the Fourier transform idea, if I take a classical function on space F, I take its Fourier transform, and then to get my operator, I kind of do a mixed sort of Fourier transform back of F tilde to get my operator. And then there's a map back the other way that's sort of inspired in the other direction because the trace is corresponds to the integral. So I'm going to put these equations up there. That I'm not going to spend a lot of time talking through them. They're there for completeness, and they're there in the slides if you want to look at them more thoroughly, or we can come back to them in the discussion. Yeah, exactly, their details don't matter, and so maybe I should have left them out so they're not distracting, but then I know people who know these things will actually want to see what we're talking about a little bit more. But I apologize for going pretty quickly if it's the first time that you've seen these things. And well, this is the point I really made above, but I do want to stress what's sort of important that once we've set this up is actually physics looks pretty similar in terms of of what you would do, of writing down an action and what you would do with it. Very good. So we had a slide where we talked about classical space-time, and then we just had a slide to talk about how to deform it. On the first slide, we considered particle localization in the classical space. Now, of course, the question is particle location in our deformed quantum space. So we're going to apply our Weyl map. So we take a classical epistemic state on the left-hand side. As I said, now working in 2 dimensions because we need the 2 dimensions to get the X and Y non-commutation here. So we take a 2-dimensional classical Gaussian, which we're interpreting as representing our ignorance of the exact location, and quantize that. Okay, so that's what the map tells us to do. So what's nice to do, of course, when you have an operator is to take a Hilbert space representation of it and diagonalize, write it down as a matrix. And it has been found that this position state diagonalizes according to the matrix that we've given here. I've given the references where this is from. I guess a special shout out to Lorenzo Leone, who was who worked on this result as part of his, I think, bachelor's thesis with Fedele. So that's what we get when you write the position state as a matrix and diagonalize it. Okay. Little philosophy. So to come to the questions of interpretation. So thinking about the quantum interpretation, if you had a density matrix written in diagonal form, then you would think that you would interpret these, the diagonal elements then as probabilities for finding the particle in the corresponding basis state. Now, these are now ontic probabilities in the quantum case. They're not just reflecting our ignorance. They're usually taken as reflecting a fundamental physical real uncertainty in the state of the particle. But come what may, they are, according to the standard interpretation, to be probabilities, and so they must be positive. So this is actually, a principle, or part of a principle will say that to be state physical, for a state to be physical, it's, when you diagonalize it, its diagonal elements must be positive because they're probabilities. So our question is rho then physical? Does it satisfy state physicality? And you can see it's going to depend on alpha and theta. Let me just back up just so 1 second. I said these are ontic probabilities, and of course, exactly what that means is highly controversial in the interpretation of quantum mechanics. We do want to stay away as much as possible from those questions. I mean, I can see there are ways we might get pushed where you can't stay away from those questions, but our goal is not to enter into that. So generally, I would say whatever you think quantum probabilities are, fill that in here. Very good. So the question of the state physicality depends on alpha, the sort of uncertainty and position of the particle, and theta, which is the area that features in the non-commutation relation. So it's kind of like the non-commutation parameter, or the non-commutation area. Okay, so that's just the matrix written down again for you and reminding you that these must be positive. And so we consider 3 cases. So there's a case where the spread of the particle is greater than the non-commutation length. Okay, and then we find, of course, the particle's not localized within the non-commutation length. And then we do find, indeed, all the diagonal elements are positive. And so this is a nice physical state, or can be interpreted as a physical state. When the particle is localized exactly to the commutation distance, then we find actually we just get a sort of 1 and then zeros everywhere else. We just get the first element. Again, that satisfies state physicality. But the crucial point, of course, is what happens when we try to localize a particle within the commutation scale. Then the first element is greater than 1, and all the other diagonal elements are less than 0. They're negative. They don't correspond to probabilities, and we see exactly our state has become unphysical. So just to sort of recap what we've got so far, and this is the first of sort of 2 results making this, 2 examples making this point. So an epistemic state in classical space can be localized, as we see, arbitrarily narrowly, but in a non-commutative space. That's why I like to say quantum space. Saying non-commutative too many times, your tongue gets pretty tied. But in quantum space, the corresponding ontic state becomes unphysical if you try to localize it within the commutation scale. So that just means these particle states cannot be arbitrarily localized in quantum space. Okay, and so insofar as we're getting at the notion of area, minimum small areas and ultimately points, they're not physical in this sense. So just an aside, if you try to actually go and calculate the expectation values for position, as we did on the first slide, of course, the particle's still going to be localized at the expectation value for x is the same. It's still localized at the center. In fact, the quadratic term is also unchanged. This is a sort of an artifact of the symmetry of the Gaussians that we've chosen, and wouldn't apply if we didn't use a Gaussian here. But you can see things going another way. You can see what goes wrong when you try to localize within the commutation, the non-commutation scale. You could take the 4th power of x, and you'll see that that would have to be a positive number if this was to make physical sense, and it's negative. Okay, so there's other ways that the problem shows up. Okay, so I want to come, what we're going to do in the second half of the paper is come at the same idea, the question of a minimum distance, from a slightly different angle that I hope we think, well, both should make the same point, but we'll illuminate what's going on, why particle localization is failing a little bit more clearly. And so to do that, there's a little bit of an interlude where I'm going to just introduce a little bit more of the formalism of non-commutative geometry. And in particular, it'll be helpful here to stop working in the more algebraic formulation that we were just looking at and go to a concrete representation of non-commutative geometry. So the full Weyl representation. And so the idea here is going to be take a regular, continuous differentiable classical manifold. We'll work in 2 dimensions. But to get a representation of the non-commutation relations and then the algebra of functions of these things, we're going to introduce a new product, the star product. And what we want to do is define a new operation on pairs of fields that has the following characteristic, that x star y minus y star x equals I times theta, so that with respect to this new product we're going to introduce, the commutation relations are satisfied even on a classical manifold. Okay, so there are different choices you can make. The one that people usually make, it's for various reasons of convenience, is the Grunewald or Moyal or just Moyal star product, which is defined the way I've as written here. Again, I don't have a lot of time to say much about it. You'll see there it involves a sum. We get the dot product, the usual pointwise dot product, plus a sum. That involves derivatives that are going to kind of kill off terms eventually. It's not going to be an infinite sum if I have a finite polynomial, because the derivatives are going to kill terms off eventually. And we've put it in a slight, the theta I, so theta ij is going to be the commutation parameter between the ith and the jth coordinates. Okay, again, we could talk more about that later, but for many people, this will just be familiar, telling you which product we're looking at. Okay, then once we have this product, one can now build up the rest of the algebra. So take it, take a classical polynomial in x and y, and to find the corresponding element of the non-commutative algebra of the non-commutative geometry, we just replace all the dot products with star products, and you just construct polynomials with respect to this multiplication. Okay, and that will now give us a map from classical fields into quantum fields. And I guess the important thing to be bearing in mind is that this star product, obviously differs from the pointwise dot product for which x and y commute. So I have the same set of functions over the manifold, but two different products that I'm considering here. Okay. So this representation of the non-commutative geometry of the algebra obviously consists of fields in a point manifold, functions over a classical manifold, and that manifold, of course, admits coordinates that dot product commute, pointwise commute. So here, this suggests an interpretation of non-commutative geometry. What's really going on is actually space is just perfectly normal. Space isn't quantum. It's just classical. It's pointful. I'd say pointy, but that sounds like there's a sort of discontinuities in it. But it's a space with points. And all that's really going on somehow is that the physics, and as we saw, the action uses the star product rather than the dot product. But space somehow really has points. We just don't, physics doesn't kind of care about them in the right way. But that can't be right. And this is sort of the thrust of the talk. You can't think that way. If you say the star product is what's physically relevant, that's what appears in the action, that's what actually governs physical dynamics, then you have already, according to the picture, the way we're trying to operationalize, think about points, you already said that points lack any physical significance. Once you adopt the star product for your action, for the physics, you are adopting non-commutativity, and we've already seen particles can't be localized once you've done that. Okay, points can't be given significance in terms of particle location because particles can't be arbitrarily localized. That's what we've already seen, and now we're going to move on to a second result to try to illuminate that.
I'm sorry, can I
very quickly
with a short question? You say you are comparing the star product with the pointwise product. If you talk about field theory, fields on a manifold, which is I guess the context here. What do you mean by an ordinary point product of points on the manifold? That thing is not defined as far as I know. So you only have products of fields, and you switch the ordinary product or ordinary multiplication of fields with the star multiplication of fields. And that's okay. That has nothing to do with points on the manifold whatsoever, as far as I understand. So can you clarify that?
So, I mean, right? The pointwise multiplication is exactly what you're saying, right? I mean, it's just x, you just multiply the two fields, the two functions at each point in the normal way. The point we're making here, and maybe this is the philosophical point, is so you can do this in the Weyl representation on the manifold, on an ordinary manifold, but once you've said the physics, in particular the action, the multiplication that you're using is the star product, you're now working in sort of dynamics and states that are in the non-commutative geometry. And we've already shown you that within that, in that context, the position states can't be arbitrarily localized. And in that sense, there aren't points. I think in the interest of time, I really should go on unless you want to say something really quick.
Just 1 second. At some point, you said you multiplied points, and this is incorrect.
You multiply at a point. That's what I mean.
Functions. We never multiply points. So the comment was pertinent, but sort of was a slip of the tongue.
Sorry, Marco. It was a slip of the tongue. We multiply at points is what I mean. Yes, I'm sorry. Trying to go too fast. Okay. And now I'm going to try to go even faster. Okay. All right. In other words, I think that was good. I mean, it's emphasized this last point. The conclusion is the points that occur in the Weyl in the manifold of the Weyl representation are just representational devices for the algebra. Okay. They're not real spatial points. Okay, so nearly there, just a couple more, literally just a couple more slides and we'll keep more or less in time. So again, so now use this Weyl representation, we can use this to better understand what goes wrong when we try to localize and consider a specific position measurement. Okay, so again, starting classically, we have our position state, localized particle state. We now want to think about an observable for measuring position. And again, we're going to suppose our detector has limited accuracy. And it's a detector that says yes, no. Either it detects a particle or it doesn't. It makes sense to model this as a Gaussian. Effectively, this is an operator for the question, is the particle localized at x sub lambda? But there's some inaccuracy in it that's parameterized by beta. It's basically looking within the range of beta around x lambda. We're working in one dimension because it's classical to keep things simple. With this normalization, if you actually set alpha and beta, so the spread of the particle and the spread of the measuring device to be the same, then you'll find the expectation value is this. And so, this has the nice result that if you measure the particle, if you look for a particle very close to it with respect to the spread of the apparatus, you'll basically, so you can think of it as going to sort of ever narrower delta function. As you get closer, the probability goes to about 1. Here's some other numbers, and we'll come back to these numbers. But suppose you, this is classically, suppose you, the spreads of you have two Gaussians that are sort of two narrow Gaussians, and you have the particle and the detector located 5 times further away than the uncertainties. Then, of course, the expectation value is going to be very, very small. It's very unlikely that you'll find a particle. So that's good too. As you move the detectors way apart from the uncertainties, their spreads, it gets less and less likely that you'll measure anything. The question, of course, is what happens in non-commutative space when we try to do this, and especially when we try to measure positions within the commutation scale. So this is the sort of second example to go with the density matrix from before. So we have Gaussians again, a Gaussian for the particle, a Gaussian for the position measurement, working in 2 dimensions. We use these as the functions. These are, in fact, what you get from the Weyl map of the classical position, state, and measurement and observable. Okay, that's a feature of Gaussians go to Gaussians in this map. So, but we're now going to use the star product to take the expectation value or to model the measurement. We'll put in the same values. So now, of course, square root of theta, the non-commutation scale, sort of is a parameter in this theory. We'll do the same thing. We'll sort of try to localize the particles within, to 1/10 of the non-commutation scale, but we'll separate them 5 times more than they are localized. And for Daylight, produce these nice graphs to show you what happens. Of course, if you take the dot product of these two Gaussians, you get about 0 everywhere because they're so far apart. But if you take the star product, you get this kind of picture. So, they're separated in I think I got this right. You can see what's happening. Okay, so we have look on the real part on the left-hand side, and say look in the x dimension goes towards the left, and the scale along the bottom here is in scales, is in units of the Gaussian width. And you can see 10 times the Gaussian width, you're still getting, appreciable overlap of these two functions once you use the star product. In other words, it's as if the detector is aware of the particle well beyond the region where the particle is, and indeed well beyond the region where the detector is. The whole thing is spread out. You get this non-local effect where the particle and the detector sees the particle, even though it's far away, and indeed is sort of seeing the particle when neither of the things are. One can take the expectation value, and you'll again find, so that's sort of showing what's breaking down in the when you try to sort of localize and operationalize such a measurement. So if you think of it in terms of expectation values, you'll also see things going wrong. The expectation comes out to be imaginary, and moments that clearly have to be positive also turn out to be not positive definite in this case. So again, the whole situation breaks down. That's one of the reflections of the state not being physical, is when you try to measure it with a measurement that shouldn't be physical, things really go crazy. The situation breaks down. Okay. Just to wrap up in 2 minutes with some discussion. So we set up what a non-commutative. So in a non-commutative space, at the beginning, we showed that the states representing, supposedly representing localization smaller than the commutation scale violate state physicality. And in an analysis of a measurement where you tried to actually localize a system within this commutation scale, things also break down. That's what we just talked about in the last slide. So, the argument is, well, given the standard assumptions about quantum probability that led us to these two conclusions, and adding to that kind of mild, what we call in the paper, tempered operationalism, not that all physical quantities are just to be defined in terms of, not that they're defined in terms of the operations to measure them, but that they should in principle be measurable. We conclude that regions smaller than the commutation scale, and especially points, are unphysical. They don't correspond to any physical operations, and so are themselves unphysical according to this sort of operationalist criterion. Conclusion of that is, when you try to do physics in a non-commutative space, to do field theory, well, there aren't any points, so it can't actually be a theory of point-wise fields. That just can't be what the theory is about, because there aren't any points for them to be point-wise with respect to. Well, this leads to a number of questions. So one would be, if it's not a theory of fields in the normal sense, what is it a theory of? It seems to be a theory of algebra, of an algebra, where the elements of the algebra aren't, there isn't some representation of those algebra that gives them, that tells you what those elements really are. The only significance they have is their role in the theory. And so, sort of question for philosophers, what kind of ontology is that? Second, there's another puzzle that comes up. If the elements of the algebra, are what the theory is about, well, they correspond, as it were, in the Weyl representation, for instance, to whole field configurations. Their point values or their values on particular regions don't have any physical significance in this as a result of what we've been arguing. Okay. The only element of significance is a complete field configuration of the function of the field over the whole space, what function it is, what its place in the algebra is. And then there's a puzzle about how to relate something like that to actual space-time measurements that do take place, not at points, but over what are apparently finite areas. How are we supposed to relate these things? Okay, well, I am out of time, so in a sense, the talk is an advert for some of the rest of the paper. These are the questions we do address in this longer paper that you can find, and I guess we're also happy to address them in the questions. Thank you.
Thank you, Nick. Thank you very much for your talk. So now I will let Rajiv Singh ask a couple of questions. And after that, everyone will be welcome to ask questions to Nick.
Okay. After that, we get to answer, right? Before Rajiv, right? So.
Okay, so I'm not expert in this subject, so I have very naive questions to ask from Professor Nick. So first of all, in your slide, I think in your slide number 2. So you're talking about the Weyl map and Wigner map. So in your page 2. So could you say something more about this? Because when I look in your paper, long paper, you have to unmute yourself.
Yeah, we can't hear you, Nick. You should unmute yourself.
Sorry. When you say slide 2, are you counting the title slide or not?
Yeah, title slide. Yeah, in
Okay.
this slide.
So go ahead with the question again. Sorry.
Yeah, in your slide 2, you have given the expression for Weyl map and Wigner map. After after this one. Yeah, this one.
All right. So not
Yes,
counting the title slide. Yes, got it.
Okay. So could you say more about this? You're saying that there is something more about this transformation.
Yeah. So I'll answer if Fidelio wants to jump in and sort of has something more illuminating to say. So we're quantizing the system, so you can see, so X and, we start with the classical system. X and Y are the coordinate functions on that space, and we want to transform them into operators that satisfy the commutation relation that we've given. And so, as one would proceed in quantum mechanics, one needs then a sort of general prescription for quantizing classical fields that respects that that commutation relation. And so the Weyl map produces that. And so it's a general prescription. So take any classical function, f of x, y, so from the left-hand side. The prescription is, take its Fourier transform. So that's the first term in the integral. And then, if you were just working classically, then to go from the Fourier transform back to the function, right, you would write sort of I, you would have I, and then in the parentheses, you'd have psi x without a hat, eta y without a hat, and take the integral to go back. The stipulation is instead, we're just going to write in the x hat and y hat, the basic elements of the algebra. and then and then the operator is defined that way. So it's a bit like undoing the Fourier transform, except we make that switch, put the hats on the X and Y. Is that what you were asking? Is that what you were asking, or you wanted to? Okay. I don't know, Fidele, is there anything more profound that can be said about what's going on here?
I'm sure there are lots of things more profound that can be said, but I'm not going to tell them. I'm not going to tell all of them, not even probably at least one. No, there is one, let me say, philosophical standpoint, is that we do have an experience of a quantum space, which is quantum mechanics. And this is, now quantum mechanics can be seen a la Schrödinger, so you have a wave function, or can be seen a la Heisenberg. Here we are definitely in the Heisenberg point of view. And what is not clear, is not really perceived by people, is that Heisenberg, so everything is in terms of operator. You can also do classical mechanics in as operators. And classical mechanics just means that your observables, so your states, etc., relate to a commutative space. So if you take h bar to 0, so your core x and p, they would be. Now, this is really something which actually personally started me in non-commutative geometry. You can describe classical mechanics in terms of operator theory. And since we know the classical mechanics is an approximation of a more correct theory, which is quantum mechanics, this is a fascinating point of view. And now this is the transposition of this idea to geometry. And one has to mention the name of Alain Kohn, because really he was the one that started all this point of view from the spectral point of view. So looking at things in terms of operators. And so this is now the Weyl map and the Wigner map. They are one the inverse of the other. They take a regular function, they were invented for quantum mechanics, and they give them operators and vice versa. Now, non-commutative geometry in general does this. Now, this is the simplest example of non-commutative geometry. I don't think it will have anything to do with the real world. It breaks Lorentz symmetry and other things. But it's a very good example also because we can use the results of the fathers of quantum mechanics. So there is a lot of technology that we can use. So this doesn't exhaust all the profound things that can be said about that.
Do you have another question, Rajiv?
Yeah. One more question is that I think you have assumed that time coordinate always commute with the space coordinates. Is it so?
Yeah. So I don't think that there's not really any sort of obvious time in the things we've done at all. But generally, I think where it comes up, that is what you'd assume, because there are kind of complications that come up, say failures of unitarity when you try to make the time coordinate fail to commute with the space coordinates. So yeah, I think that's right here.
And just a small thing is, what do you mean by ontic probabilities?
Well, that was the question I wanted to, punt on, seriously punt on, right? I mean, in some sense, I don't know, that's one of the questions of the interpretation of quantum mechanics, exactly how you're supposed to understand what those probabilities are. But generally, there are good reasons, say interference, that make you think these can't just be a measure of our ignorance. There are many arguments that these somehow have to reflect a state of genuine uncertainty about the world. Obviously, that's controversial, and there are many different interpretations of quantum mechanics where the probabilities come out to have different significance. But a fairly standard notion is that these aren't just reflections of ignorance. They're ontic. They're to do they're to do with reality and not just our kind of the relation of our knowledge to reality.
So it's a kind
Tushar wants to come in on this one too, I think.
Sorry, might I just add something small to that? Is that okay?
Yeah, sure.
Yes,
for me.
Great. Sorry, I'll be really quick. No, so I think in this ontic versus epistemic probability thing, I think Hugh Meller has a very nice sort of sloganistic characterization of the difference. So if you think of something like an epistemic probability, what you're using that for is to evaluate the plausibility or the correctness of a claim, for example, of a scientific theory itself. So an epistemic probability will allow you to assess how likely it is to be true that some claim from, like quantum mechanics is true. Whereas ontic probabilities are sort of irreducible elements of those theories themselves. So they have nothing to do with any evaluation that you might make about the correctness of a theory. They're instead kind of primitive elements of the world according to the theory that putatively describes them. And so what we're saying over here is our condition for state physicality, we're using the switch from epistemic to ontic probabilities to make the metaphysical point that's encoded in the state physicality commitment.
Well, I think now we have time for discussion and other questions. Maybe, Nick, I would suggest that you stop sharing your screen so that we can have the face-to-face discussion. And there are several ways to ask questions. You can raise your hand if there are many people. Otherwise, you can just unmute yourself and ask a question. And you can also put your question in the chat, and we'll see how it goes. All right. So, Francesca, I see your hand is raised. So if you want to go.
Yeah, I just wanted to intervene with interjecting with a comment at this point about the interpretation that non-commutative geometry is suggesting with respect to quantum mechanics. So a point that I tried to make in a strong way before is that whatever interpretation you are evaluating in quantum mechanics, it would be better to be consistent with the rest of the knowledge that we have of the world from contemporary physics, in particular with general relativity and with quantum field theory. So you want an interpretation that is not just an interpretation of quantum mechanics, but it's an interpretation of the quantum theory, including quantum field theory. So different interpretations put the accent on different aspects, and I think I can join Fedele, I don't know, Nick here, in putting the stress on non-commutativity, and non-commutativity is somehow the other face of the medal of discreteness. And taking the point of view of Heisenberg is certainly, as Schrödinger itself recognized in the end of his career, is the right way to go. Then, okay, so what is the ontology that is compatible with this? I have been working in the framework of relational quantum mechanics, in which the ontology is not on objects, namely not on particle, but on facts, interactions, and so on. So I would like to suggest that maybe there could be a nice convergence between the perspective of non-commutative geometry and the ontology suggested by relational quantum mechanics. I don't know if you have thought in these terms, Nick and Fedele, before.
No, I read what you did, but I see that there is of course, putting together quantum mechanics and gravity is the problem. Somebody had mentioned time before. It's an embarrassing question. Time is an embarrassing question because everything here is Euclidean, is in general mathematically compact, etc. So there are things now. There is no time to discuss things. But people are trying. We are trying in the non-commutative geometry community, other communities, to get time in crime spaces, etc. So definitely, as a physicist, I think that the philosophical point of view can actually help us physicists. I know that Francesca will agree with me, but not many people will do that. In the sense that we should probably start asking this kind of questions: how in fact, discreteness and non-commutativity, how they get together. I don't know, other than telling that we should keep on talking about these things, it's, I have nothing really concrete to offer at this stage.
If Nick has no thing to add, then Patrick has a question. And then there's Marco and Philippe also, I think you have a question. Okay.
I would like
I guess I'll just say I hadn't thought about things in those terms. So in fact, I don't really have anything to add right now to what, Fidele said, but yeah, let me think about that.
So, hi, Nick. Very much enjoyed your talk. So I think this is really interesting work. And I've got kind of a bit of a naive question about how it's related to other interpretational questions. So when you go through this process of identifying this whole tempered operationalism for how you can pick out points in space-time, and then you eventually talk about how you can't perspicuously do that in the deformed algebra. When you show that plot of those, what I would hesitantly call something like a non-local influence, because you see you're making a measurement at one point and you're obtaining a probability for something that's actually located at a different point. It's non-locality, not necessarily in the ordinary quantum foundation sense, but there's a certain kind of non-locality that seems to be coming up there. And I'm interested in kind of how that's related to the sort of non-locality that you see in the Bohmian picture, where you have a guiding wave and you can see the probabilities at one point are also influenced by probabilities at other points. So you've got the same kind of non-local character going on there. Perhaps I'm missing something fairly straightforward, but I'd be interested in hearing your perspective on that.
Yeah. So something like that is going on. So I think, I don't know, to what extent one can sort of push this, right? I mean, because, and I'll invite Fidele to come in on this. The relation to the Bohm I would point out is, so in Bohm, you have the theory is the wave function's really living in configuration space, right? And so the coordinates, in fact, there is locality at that level. It just appears non-local when you project down into ordinary space, because you have x1 over here and x2 over here, and you're not noticing that there's a point where they coincide in configuration space. And that's not kind of what's going on in this case. It's all kind of living in space. So insofar as, there's sort of influence between the points kind of going on here when you multiply them. And the reason it's there is, of course, because of the star product that's introducing this non-locality, that's actual kind of interaction between distant points that's going on. It's not this business of having a larger space and projecting down and losing the locality. Okay, so it's different in that formal way, and so maybe, but otherwise that low distant points are kind of interfering. Fidele, does that sound okay with you?
Yes, but yes, I think that if they have no points, you cannot have locality, and so any quantum theory will not be local in this sense. But Bohm and hidden variables or guiding wave, etc., they are a different kind of non-locality. In fact, they somehow, from what I understand, is they are non-local because there is a superior locality. This here instead, it doesn't really make sense to be local, because local means that you are at a point, and here you don't have these points anymore. So So you can interpret this in some non-local theory, but as we discussed in the paper, it's really the lack of points, and therefore lack of locality, because you have no point.
Right. So I guess I guess you could kind of make the claim that even in the Bohmian picture, you can still have a well-defined notion of points, even though you've got manifest non-locality, on the basis that that non-locality is kind of on this projection, not in configuration space.
Exactly.
Okay, so the lack of points is really genuinely special,
yes.
the deformation algebra, and not, yeah, okay, cool.
Yeah, that's good. That's actually helpful for me to think it through. Because of course, in those graphs, we're sort of supposing for reductio that there are points there, that this is what would, suppose there's the manifold. What actually happens if you try to do this? And what you're really seeing is that assumption is not really a good one. And so there isn't that. Yeah, that's much better. Thanks for Daly. Yeah.
So now maybe Marco, then there will be Philippe and Marius.
Okay, so first of all, sorry for interrupting in the middle in the middle of the lecture. It was really, my question is about the traditional motivation for this whole approach. As I understand, what used to be the main motivation was the idea that you want to smear the points in certain way to make them fuzzy, in order to regularize the theory, to make to tame the divergences, the ultraviolet divergences in your theory. And as far as I'm informed, this kind of idea sort of failed. I mean, the divergences still appear, and they are even much worse than in ordinary field theory. So my question is there a way to first of all, to make this, first of all, do you have any alternative motivation to do this kind of program with non-commutative geometry? And second, is there a way to circumvent the issue of divergences in the theory? I mean, can you I mean, compared to the ordinary classic, I mean, quantum field theory?
No, I can answer.
Okay.
Historically, it was believed that ultraviolet divergences would be tamed. As you say, it is worse, not in the case that there are still some ultraviolet divergences, but now we have some unwanted infrared divergences due to the fact that the theory is non-local, as we were saying before. But however, this has to do with the usual Moyal product, which is the one that we use. As I said, I do not think, certainly not now, but probably not even at the beginning, that this is really the theory of the world. So multiplying fields with the Moyal product is really a naive way. It's using a tool which worked well for something else, which was phase space for space-time. And therefore, for this kind of considerations about, say, philosophical, so the big thing is still the best way to think about them, because it's something, as I said, in which you have a very good technology to talk. It's a well-known and well-defined non-commutative geometry. Now, the non-commutative geometry, which will be probably used if we ever, I hope I'll see something like the quantization of gravity, but it will certainly be different. And in fact, in general, we meet with people that do strings and loop quantum gravity. Actually, in non-commutative geometry, managed to talk with both communities. And there are inputs from there. And there they are probably more advanced, more complicated. Their space-time is completely loop quantum gravity gone away, but it will be something like that. So field theory can still be there. I want just to mention that in Cohn's approach, which is spectral, the spectral action has a cutoff, as a regularization of the theory, and that one has other nice things and problems, but there is probably more in that direction that one has to look. But all this discussion that we are having, we are for It's like describing physics and talking about the harmonic oscillator. Things are not harmonic oscillators, but if we talk of harmonic oscillators, we know what we are talking about, classically, quantum mechanically, and something like that. So it's the example of that. Yeah, I don't think now that the Moyal quantum field theory is really there are still interesting things can be said, but it's like going to the gym. And now probably we should go out and try running in the open. Now we cannot do it because of COVID, but do something more real. But the basis is better to do it with on the under control, something that is better under control.
Thank you.
But the idea is we can work in that framework to sort of get to the core of the problem with points, and the things we're seeing in this framework, one would expect to also apply to the fuller framework.
So now Philippe, then Marios, and then Steve.
Okay. Thanks for the talk. So this is going to be, I think, pretty naive question, but like throughout the talk, I was in my mind changing y for p, and then everything made sense for me in terms of like Wigner functions, and then it would be just, you could make the same claim that the phase space of a particle in quantum mechanics is a non-commutative space, and there's no points in it, and so on. But now it seems like you're having y as being like really a position coordinate. And my question is, well, what happens with momentum now? Because then presumably there should be momentum in the x direction and in the y direction. And how do they relate with this already non-commutative coordinates? And what's their commutation? Like, do they also satisfy the canonical commutation relation with their respective coordinates?
We didn't put h bar in the game. So we are only looking at configuration space. Now there is a difference because x and p are two different objects. No, one is a momentum, one is a position. X and y, they describe space-time, space, not phase space. And but the technology is the same, but we are used to the fact that we can see position but not velocity. Now the point is that we cannot see even position, but the technology is exactly the same. It's everything we are using has been in fact developed. Most of it, Moyal product was introduced for quantum mechanics, but there is the space. There is something more, no? Because they are the same. There is no symmetry between x and p. Yeah, Born, you can do some rotation, but you don't rotate x within x and p. Say q and p, to avoid confusion. Q and p, you don't rotate one into the other. Instead, x and y, they are the same object. In fact, you can rotate one into the other, and they together will do space-time. So we are using a known technology developed for phase space for the just space. Now there will be, of course, if you put kinematics in it, so time and evolution, and so you put fields. So the correct way to think is always in terms of quantum field theory. So you put fields, and then these fields will have their duals and so on and so forth. So you put derivatives, and then the correct way of doing this is to do through a differential calculus. Now every non-commutative space, Kappa-Minkowski, Moyal, etc., they have their own differential calculus, etc. Because the momentum is derivatives, but that would take just to answer the question would take a long time. But this is just the space. Then you put a differential structure in momentum, and this can be done. In fact, in this case, it's quite simple because derivatives still satisfy Leibniz, etc. So that's why Moyal has nice things. Other models like Kappa-Minkowski have differential structure. The space-time there is curved. The phase space, the momentum space, I'm sorry, momentum space is curved. And this creates a lot of mess and nice mess. But that's it's another seminar that other people do better than I do.
Thanks. Then I would have a follow-up question. So if I understand correctly, then this is the space, and actually the quantum system should be some version of a quantum field living on that space. But then why did you, in this work, looked at the X and Y operators and tried to represent them on a Hilbert space, and then you used the sort of normal, it seemed to me, you use the normal quantum formalism on these X and Y operators, and you make density matrices over the Hilbert space where they act and so on.
Yeah, because, well, because this is, we put a Hilbert space structure on the, there is no really Hilbert space, but the operator and density matrices. And we don't have states are, we do it at Heisenberg, so we don't have the wave function more. But this is done essentially in non-commutative geometry just to quantize space. No, then you can do quantum field theory on this space, but it's a further level. But now philosophically, we want to understand this space. We are used to a space. Space is where things are, where you can put things, and the field is a distribution on this space. Now, the point is that we don't have this space anymore. We cannot have it anymore. Then you can always have functions of these operators and do quantum field theory, and people have done it. But the point, see, in the paper, there isn't any particularly new physics, but there is the attempt of describing of this, what is space in a non-commutative space, so that a space which has no points. Then you will have fields on this space, which is probably the thing to do, and do calculations, etc. But we shouldn't lose track of what is underneath. And underneath is this complicated object, which has no points. It can be described by operators. So, but then is the quantum mechanics one? Yes.
Can I come in on this? I think I heard something else in kind of Philippe's question that I wanted to kind of get to. So, and I think, you know, I think as I said in the talk, when you have the quantum space, you still have a choice about, you know, it's ultimately, or the way we set it up, basically a theory of fields. And you can choose those fields to be classical in the sense that they're sort of Hamilton principle satisfying, or you can choose them to be quantum in that they're path integral satisfying. I don't know how one would just put a particle, you know, a classic, so, but, you know, so from that point of view, you sort of start with classical fields and move to quantum fields in the, sorry, that's not quite, I'm mixing two things up here. When you think about the, so there's that was one point I wanted to make, but another, I think, to go to what you're saying is, you know, this framework, the quantization map, requires you to start with a classical field and quantize that to go to the quantum space in the Weyl map. I don't think that it's not a prescription for a point particle that you get to quantize. So, you know, we're starting with this classical epistemic state, in part because we need some field that we can actually quantize according to the prescription. So one thing is, you know, we sort of have done the quantization of a particle already to get to the non-commutative situation, and because we've chosen that epistemic Gaussian. So then if one wants to, so that's partly what's going on here. There's not a case where we have a sort of point particle and we write down its states. We have to approach it in this other way. And then the other, you know, I think, so the other thing, the second point is, as I say, so once one's quantized the space, you still have the choice about how to, you are working in the field theory sort of context, but you could think of these as classical fields in the sense that I've said. There's no H bar, they satisfy Hamilton's principle, and then quantize them, and then you would get to something along the lines that you want. But it's not a case that's quantizing classical fields in quantum space-time, promoting them to quantum fields in quantum space-time. I don't know what it looks like to have a particle in quantum space, really it doesn't make sense, right? To have a point particle in quantum space-time, because there's no points that it could be to which it could be located. So that's sort of the story I think that you need. Is that okay?
Can I just, I don't want to say too much, but if I understand correctly, a classical field in a quantum space-time is like isomorphic to a Wigner function on normal quantum phase space for a single particle.
If you change t into y, yes.
Yeah, yeah.
At the formal level, not an interpretational level.
At the formal level, yes. And at the interpretation level, yeah.
With this non-commutativity, if you have kappa Minkowski, no, you would have to do completely different things if you have loop quantum gravity or whatever. So this is the simplest case is this one. In this simplest case, yes.
Okay, thank you.
Marius, would you like to go ahead?
Sure, thanks.
Sorry, can I just interject about this? I'm sorry, Marius, I apologize. Just to a short comment related to this previous question, actually to Nick's comment. I just wanted to say that the whole approach of quantum space, as presented here, requires you to have at least two coordinates, like at least a two-dimensional space that should be in a non-commuting relationship. Quantum mechanics, as such, has the zero dimensions of space. It has only. I mean, if you look at the space-time counterpart, it has only time, right? So in the Heisenberg picture, the quantum operators depend only on time, right? In quantum mechanics. So it's really a zero-dimensional field theory. So there is no there are no coordinates to commute or fail to commute in quantum mechanics. So as far as space-time goes. So this is really a field theory concept. It has no counterpart in quantum mechanics in its concept at the formal level, at least.
Marius?
So first of all, Nick, thank you for the very nice talk. Very interesting. I am a bit confused as to what exactly is your conclusion there. I mean, I admit I didn't understand exactly what's going on with the formalism, but that's not what bothers me. What I don't understand is what you mean by there are no points. Not because I don't agree with the statement, but I don't understand how this, whether I think it does go further, whether it goes further than what we already knew from the classical theory. So you're probably, you know the whole argument that because of the equivalence of diffeomorphisms and changes of coordinates, there is an argument to be made that was made a long time ago by Dirac, if I'm not mistaken, that points of the manifold do not have any physical meaning by themselves. And one has to talk about coincidences. So I was wondering whether you are saying that coincidences don't exist, or are you really talking about the manifold?
Yes, what a nice question, bringing those two things together. That I think we even mentioned the whole argument, but we didn't bring it to get them together in that way at all. So, okay, I mean, so off the top of, so a couple of things. I mean, so the first one is, I mean, I don't know quite whether there's sort of different interpretations about what the whole argument shows. whether you actually have to have sort of general covariant, you know, has to be like a generally covariant theory before you can bring it to bear, or whether you're willing to sort of, I mean, there's a sense in which you can have, you know, as long as you're willing to apply the diffeomorphism to the metric, even if it's a Minkowski metric, then you can get a similar whole argument going. In other words, it's a question of what you take to be fixed and what you're prepared to actually act on with the diffeomorphism. So one thing to say is, you know, the cases we're thinking about here, they're not, there's no dynamics in the geometry. For instance, you know, we'd be thinking that this is, say, just, you know, totally flat space-time. So there isn't sort of general covariance here. So in that sense, you might say the whole argument isn't applying to this case, because it's like trying to apply the whole argument to Minkowski space-time. And often people don't think that applies. You have to have a, you know, the more general framework where the gravitational field is dynamic as well to make sense of applying a diffeomorphism to it. The other point is, but suppose you are, and so you say, yeah, what are you telling me? And I think you put your finger on it. I think I want to just say kind of exactly yes to the way you put it. That seems right. If you want to say, yes, sure, that the whole argument still shows even in sort of Minkowski space-time that there's no points aren't individuals. There's no points in a, you know, you can't think of them as things, and you really should focus on the coincidences. I think that's exactly right. And I think that, I mean, that seems to be what one is exactly would, I mean, I guess our measurement is slightly different in it's sort of showing what it's sort of suggesting is these things coincide, even though they're not at the, you know, if you tried to think that there were points, you end up, sorry, excuse me a sec. You end up thinking that it ends up looking as if the measurement apparatus and the point and the particle coincide, even though they don't in the space, and so sort of indicating that there's something wrong with the notion of point coincidence in this framework. And you know, and then we get to the conclusion that there really aren't points, there aren't point coincidences, because they don't kind of make sense if you try to act as if there are. Does that help? I'd be really interested to know what Tushar and Fideli have to say after you as well.
It's a difficult question. Nobody knows how to think about this, right? Yeah, the reason I ask is because I know that people are thinking about quantum reference frames, and an idea there, I don't think it's clearly demonstrated, but somehow is that, as you say, there is a coincidence, there is two particles meeting. There's going to be some observer that sees that. For him, that's a point. So when you say that these things don't exist, I'm wondering whether it's about not existing objectively, in the sense that some observers might see them as points, but others might not, might see them as a superposition of being in two locations, for instance. Or is it a more absolute statement that you're making, that there is nothing in nature that you, even in classical theory, I guess, in classical theory, by which I mean, so the superposition of two classical trajectories. You're in quantum theory, but you still have classical paths. And then I take another superposition, and I can talk about these paths crossing, and that would be a point. But you're sort of saying...
yeah, but can you operationally see the point? You see, there can be points, but sometimes I have another metaphor of mine. The machine in the ghost. Not the ghost in the machine, but the machine in the ghost. If you want to measure something, you need a machine. You need a device. Now, if you have this toy model, your measuring device is a function. We play all with Gaussians. Everything was done with Gaussians because I could do integrals exactly with Mathematica, and they could produce the pictures in a few seconds, all of them. But see, you say the two paths cross at a point, and so that is a point. And also path integral, you have a starting point and ending point, and so on and so forth. But you have to measure these things. You have to to have an operational and a mathematical counterpart. And we are working here the mathematical counterpart. What I call a measuring device. An experimentalist would probably look at me with like I'm crazy, probably I am. But so the points are there or not? This is the question. No? So this space is made of points or not. But if I try to look at them mathematically, and so no problems of technology, I cannot. So therefore, this is the philosophical question. So we use another word that's too sharp, meaninglessness. So points, they have no meaning, but they are there. You need them, you use them, but they don't have an operational meaning. And now, philosophically, this has to do with the ontology that was mentioned before. So it's a necessary ontology, but it's not there is no physics in this objects. So this is.
Can I? Sorry.
Yes.
Sorry. Can I just add something small to that? Just about I really like that you brought up the whole argument, because I think the argument that we want to make here, I think, highlights an important consequence of the whole argument. And actually, this is something that I learned from reading all of Nick's papers on, among other things, relationalism and the whole argument. So the whole argument is ultimately not directed towards any claim about what you might call a domain of quantification. It's more worried about claims that you might make about the identification of points across different possible worlds, right? Because the whole argument is basically saying something like, if I took everything and shift, it's a version of the Leibniz shift argument, right? If I took everything here and shifted it a certain number of feet to the right, would there be a difference? And that's asking if there's some notion of primitive transworld identity. And you can still say, no, we in our best theories, we're going to quantify over points. We're going to say points exist, but one of the properties that we thought points had, namely that I can point to a point in this world and say, this is the same point as the point in some other possible world. And so I can then make a distinction between these two scenarios. The whole argument tells you that, you can't do that. And of course, you might go further and say, well, then I don't want to quantify over points, but you can nonetheless still tell a consistent story about quantifying over points that's consistent with the whole argument by just denying transworld identity. I think what we're doing and what we want to say about the pointlessness of non-commutative geometry is that on the basis of certain arguments from what Nick spoke about today, from tempered operationalism, in the paper, we have another set of arguments about the formal notion of definability and meaninglessness, which are more semantic notions. The point that we want to make there is, I should stop saying point, but the point that we want to make over there is that the domain of quantification is itself one that's not going to incorporate points, because arguments that you might have in commutative theories for why you should quantify over points don't generalize to the non-commutative theory, but that's only under specific assumptions about how it is that we arrive at what the domain should be. And so, as I said, in the paper, we have two suggestions. We say, well, we can arrive at a domain of quantification by considerations of operationalism, or we can arrive at it by considerations of formal definability. And in a sense, these considerations are orthogonal to the whole argument, because the whole argument has kind of assumed that we've already made that decision about what goes into our domain. And now we have to make the further argument about what the properties are of those points, in particular modal properties about possible worlds. So that's all I wanted to add to that.
Very quick, thank you very much for the answer. Very quick follow-up. So points do not exist, but it's also a mathematical abstraction at point, right? Does an approximate localization exist within the certainty principle? So small neighborhoods around the points.
Sorry, we're talking. I didn't quite get Sorry, was that in the non-commutative case? Do you mean? Or?
Don't exist. I mean, I can also understand this as saying a one-dimensional line is never realized in nature because everything has some width, right?
There are no limit in thinner and thinner lines. There is no scale, so an absolute point will never exist, and I can never measure an absolute point. But I can always have something which is more and more closer to the point, because you don't have a scale. If you have a scale, then you have a minimum. So it's on a lattice in a discrete space. You would have that there is a minimum, but this is too naive. So this Pythagoras. But here there is no Pythagoras, because you can be arbitrarily close, but it's the meaning that the point that in non-commutative geometry as opposed to commutative geometry is profoundly different. So everything is an abstraction. There is not the point, the field, etc. But here it's as a further layer of not existing, because there is a scale, of course.
But I guess the question is there? I mean, you can ask two questions, right? Is there a theoretical limit by the standards of your theory, independently of what you can build, to localization? And in classical mechanics, and even in ordinary quantum mechanics, on defined on just regular sort of quantum mechanics on a commutative space, the answer is there's no theoretical limitations by the lights of what goes into the theory about what the smallest area is, or the smallest length is. But the same thing can't be said for a non-commutative geometry, because even by the light of that theory itself, all of the claim is something like all of the arguments that you might have in quantum mechanics for saying quantum mechanics on a commutative space, for saying that I guess metaphysically we can make conceptual sense of a smallest of a point. Those arguments don't generalize to the non-commutative case. I think that's the sort of the distinction that we had in mind.
I would suggest that. Okay.
Can I just actually? There was something else Fidele said earlier that I wanted to respond to, sort of on behalf of Marios, if he doesn't mind, because I think Fidele was asking, was challenging you to give a kind of operationalization of point coincidences of two particles, coming into contact. And I think our last, the two Gaussian case is pretty close, is in that direction already. Just interpret those two Gaussians not now as a measuring device and a particle, but interpret those as two particle states. And exactly what we're seeing is, what we're starting to see there with the star product is, look, they're coinciding even though they're way apart from each other. And so that is sort of showing how the notion of point coincidence is breaking down in non-commutative geometry. I mean, it's kind of what I said at the beginning of the answer I gave before. I now have two Gaussian packets, but they're now overlapping, even though, they're overlapping in the quantum space, even though they seem to be, 5 times further apart than their widths when they're that small. Okay. And so that's to sort of say, I can't make sense of a point coincidence because they start to coincide when they're, way apart. They're nowhere near at the same point. And so that's sort of to help you see how the notion of point coincidence is breaking down. It's not a story that brings in observers. So I don't think that part of the story is happening here. It's just in the states themselves. When you asked about different observers, I thought Fidele was going to start talking about Kappa-Minkowski here, because I think then you do get kinds of weird observer effects like that. But I don't think that's what's happening here.
Thank you. I will leave the rest to...
Yeah, I would suggest we move to the next question by Steve, and then there will be Gaetano.
Okay, Nick, thanks for the talk. I'm coming to this from the direction of point-free topology, and so my question might be rather naive from a physical point of view. But in point-free topology, there's a story to be told that the topology embodies an account of how you observe the points. So, for instance, with the real line, the observation, if you say the observations are that a real number might be strictly less than a rational or strictly greater than a rational, then you get both the nature of the reals themselves as Dedekind sections, and you also get the Euclidean topology coming on them. But actually, in real life, it seems that's not quite how you observe real numbers. You don't have this crisp boundary of being less than or greater than a rational. Instead, you measure them with Gaussians. So my thought was, if you take a physical situation where you're trying to measure a dimensionless real quantity, such as the fine structure constant, and you're trying to get that as precise as possible, you will be doing that using, I guess, some kind of Gaussians from the experimental setup. So my question is, do we see any phenomena that are analogous to non-commutative geometry that might suggest somehow we're mathematically dealing with the wrong real numbers from the physical point of view?
So Fedele is, I hope, more likely to have some thoughts on this.
It's a tough question. I'll let you answer.
Well, I think it's Tushar's turn, isn't it?
No, I was the last person to say.
Yeah. Okay. I don't. Yeah. I guess I don't know enough, or I guess I don't know about point-free topologies to have any kind of meaningful thoughts on this.
My question is,
I mean, I guess the thing to say is, so maybe just to go, if you want to say, if you have some idea, if this was sort of rhetorical, I'd be really interested to hear. But let me just sort of say, just sort of say again, when we did start with the classical case, and we sort of imposed, we assumed one would assume, your measurements are, always having uncertainty, and we modeled that with Gaussians. But that, just putting the Gaussians in didn't take us out of the classical space by itself, because we can just take the Gaussians to be as small as we like, as Fedele was saying. So, we never reach points, but there's never any smallest point. So introducing the Gaussians by itself didn't get us to the non-commutative space. We introduced those so that we can model something in the non-commutative space. But I think that's about all I can say. Did you have some sort of thoughts?
Me? Did I have thoughts?
Yeah.
No, I think I wanted to present what looks like a physical situation that physicists might know more about, which is, measuring something like the fine structure constant as an absolute real number. What can you actually find out about it? And do you get, where does quantum mechanics sort of put qualifications on the kind of answer that you might get?
Can I chip in just for a moment? It's there is this notion in non-commutative geometry, at least in this framework that Nick presented as a field theory with the Moyal product and all that. You can actually interpret that theory as a theory over a classical regular space-time manifold of commutative points, which where the dynamics of the theory would be very, very complicated and non-local. I mean, you can really expand on all the Moyal products in terms of ordinary products. So you could interpret the whole, if you build physics in this way, you could interpret it as very complicated physics with very complicated dynamics over a regular commutative manifold that we're used to. So if you think about building some kind of a theory like that, in understanding the theory in that way, it is likely that this kind of approach would give some type of correction terms to the calculation of the fine structure constant, because at some level it will be different from ordinary quantum electrodynamics or this kind of something. It would be non-local theory and complicated theory and so on. But that is, as far as I understand, that is an expected feature of any kind of approach like this. It's supposed to have something like quantum corrections to whatever we were building. So in that sense, this is regular and expected. But as far as this has nothing to do with topology, as far as I understand. I mean, nothing in the standard sense of whether we should change the topology of real numbers or something like that. I'm not familiar with that kind of interpretation.
Well, I'm sort of having from what I know of Con's knowledge, he might be prepared to go to a topos instead of a topological space. In other words, a generalized topological space. So there's sort of open opportunities there, but I don't know where they would go.
I don't know. I can make your question more difficult. You are talking of the fine structure constant. Now, yeah, whatever the exact value of the fine structure constant is somehow irrelevant. But there is something which I don't know very much about, that the whole conductivity. Now, the whole conductivity for the anomalous Hall effect, it's sensitive whether the quantity is rational or not. So I always thought that it's physical quantity. It doesn't matter whether the number is rational or not, because I just know if I have to tell you the number, will be just with a certain number of digits because I measure it. But now the whole conductivity, theoretically, there is a difference whether the number is rational or not. Now this is a very complicated thing, and I'm just asking a question more difficult than the one that you are asking, because you are asking how do I measure things in a topology without points, and yeah, I don't know. It's a fascinating question, and but I don't know really.
What was the phrase you used? Whole conductivity. It
whole
sounded
conductivity.
Like...
Yeah.
Whole.
H-A-double-L.
Okay.
This is a well-known effect, and Nobel Prizes have been won. But if you do the theoretical analysis, it's sensitive whether whether a number is real or rational. No, because in some cases you have some effects and some other. And I never understood really how to translate this in terms of measurement. So. Right. So I don't know. So this is another it's another worse, more nastier version of your nasty said with admiration, of course, question, in the sense that we still have topology, even if in a different way. Miguel van Nijmark, and so there are still topology here. Now you are going to a pointless topology, which is a further level, and topos and this kind of things. And
yeah,
I don't know, I can claim it's late in the evening, or those of us that it's a fascinating question.
There is still one question by Gaetano Fiore.
Yes. Can you hear me? Can you hear me?
Yes, we can.
And now you can also see me. Thank you, Nick and Fedele, for the very nice talk, interesting talk. I have two questions, one more philosophical and one technical, on the model of the Moyal-Weyl model you have considered. If I understand well, the philosophy, the goal you are pursuing using that model is trying to find a way to avoid the unphysical states and unphysical observables which you have found at the end. So you would like to look for a theory, self-contained theory, which automatically excludes observables and states, which would lead to a localization smaller than square root of theta. Is that correct? And as far as I understand, you don't succeed. Is it correct? But the goal would be that one.
It's an
I don't.
Go ahead, Nick.
Sure. I mean, that's not. I wouldn't quite put the. That's not the goal of the paper. I would say. I mean, we set up the framework, and of course, it shows that formally
no, I didn't
those
mean
systems.
of the paper.
Right. Our goal. So presumably, if they're not there, if you developed a framework in which they didn't exist, then right. I mean, you still don't have the localizations. Fidele, did you want to add something?
Just to clarify, I didn't mean the goal of the paper. I mean the goal of developing a physical theory of non-commutative geometry would be to build a setup which automatically allows only for physical observables, so that the unphysical ones which you have found do not pop up.
Well, more modestly, we show that points are not part of the ontology of your theory of what you have there. So this is more. So the goal is not to show that there are no points. It's missing the point. The point is missing the point. So many points.
Yes, but the states you consider, these epistemic states, which are Gaussian states, you see that they make sense as long as the spread is larger than square root of theta, and then they lose sense. And but there is not a built-in way to exclude them. You have to exclude them by hand, so to say.
Yeah,
to avoid
I mean, it's a bit hard to see. It's if there's going to be a quantization map between the classical and the quantum, I think for me it's hard to see how you would end up excluding them, because they're perfectly respectable functions in the classical space-time, and so any quantization map is going to map them into something. So
but at least for me, a reasonable goal for a non-commutative geometry would be to build up a self-contained theory which automatically excludes such situations, so that you don't have to put an ad hoc, so to say, rule to exclude this situation. So at least this would be my philosophy, and maybe it's also yours. And of course, you did, which is a very simple model, is very instructive, because it says that apparently it's not so easy. But exactly on this model, now I have the technical question. I mean, if I go back to the epistemic state, the Gaussian, if you do the transition from rho to rho hat, so rho, you have the Gaussian over x squared plus y squared, and you get, and you would, if I understand well, the non-commutative analog would be with the hat on both x and y. Is it correct?
Yes. Yes, while quantization.
And then and then you represent y through derivative with respect to x.
No. So if I go into the number, I do the matrix in the number operator basis, the harmonic oscillator Hamiltonian basis. I take a discrete basis, and I take the one of p squared plus is the number operator.
And you find that
I find a matrix, and this matrix is
rho hat is
it's a matrix.
Yeah, which is no more positive definite.
Is not.
Which is not no more automatically positive definite.
It's not a density matrix. It's not if I diagonalize it, it has negative eigenvalues.
It's not positive definite.
Yeah, the trace is still 1, but it's not positive definite. It becomes.
But the technical question is if there should be in the right-hand side. I mean, since the derivative with respect to x is not a negative definite, there should be a minus sign in front because coming from I square. So still,
if you want to go to, it depends which basis you want to go. I prefer to go into the A and A dagger basis. So you write X as A plus A dagger and Y as A minus A dagger. And then I go to the discrete basis. Matrix, I need a discrete basis. So I need an operator with a discrete spectrum. Now this is really technical, but I take as operator with.
I have the impression that the exponent.
Fedele, is it Giovanni? Sorry, it just says G.
No.
Gaetano.
Gaetano. I think Gaetano's talking about a different equation in the slides. I see where you're looking, where we actually do the Weyl quantization. And you're saying in the exponent there's x. We write x squared plus theta squared dx squared, and you're saying that should be a minus.
Yes. Otherwise, it's not positive definite. The exponent as xy plus y squared.
So I think that's probably a typo in my
It's
slides.
probably a typo, yeah.
Okay.
Maybe you can share the slides again. So
I mean,
see.
Sorry, my question is if because x square plus y square, or if you want x square plus theta square p square, so it's right positive definite. So also the Gaussian must be positive definite.
Okay, no. That is definitely a typo. That is definitely a typo. Yeah, this is a typo. It's minus. It's the Laplace, the harmonic oscillator Hamiltonian. So this is just a typo. Thank you.
Exactly. Okay. But then how can you get a non-positive definite rho? Because you are taking a Gaussian of something positive definite, and so it should be also positive definite. I'm a little puzzled by this point.
You want this to be? I don't know. Now that I would have to check the calculations. I don't know. They are in the thesis of Lorenzo and also this paper by Terezinski, Eckhart, Simacic. You want to say this is an? I don't know. I am not. I'll let you know. I understand the question, but no, I suppose it's not a positive operator in that case. You cannot write it as the product of an operator by its conjugate. Because if you do the Campbell-Baker-Hausdorff, you have other terms and they become dominant. I like to think about this.
Okay. Anyway, the idea, I think, is the goal, the philosophy is very interesting. I mean, I would share, of course. Yes. Thank you.
I think we can.
All right. Yeah. Are there other questions? Otherwise, it's now close to 2 hours that this seminar has started. So let's close the seminar. Thank you again, Nick. And thank you also, Fedele and Tushar. And thank you everyone for your participation. The next QISS seminar will be in 3 weeks, and it will be Anna Pearson talking about gravitational decoherence. So stay tuned. Bye.
Yeah, thank you, everyone. Really appreciate it. It's a very good time. Bye.
Bye. Bye, everybody.
Pierre, you're muted.
Ah, ça va?
What's here? Okay, it's all the friends. What does that do?
Yeah,